So let's start. So hi, I am Bhera, and today we are going to discuss gradient operator. So as you know that this gradient operator is very much important in physics and mathematics, and uh, and uh, and it appears in a lot of a lot of important equations. For example, immediately I can think of Schrodinger equations. So there is this del square operator that if you write the Schrodinger equation in the position basis, then you have the momentum operator as minus is cross del operator. So the other equations are, for example, if you heat equation, there is this gradient operator. Then you have your wave equation. There you have a gradient. There you have your gradient operator. And all the conservative forces in nature are also expressed as a gradient of some potential. For example, the gravitational force is also a force which can be described in terms of a potential, and therefore the force is nothing but the gradient of potential energy. So it's very very important, but we are not going to discuss that in that context of in that context. What we are going to do is that we are going to discuss in basic terms what does a gradient mean. So if I give you a function f of x y, and let's say the function is like x square plus y square, and I tell you to compute the gradient at 1 comma 1, so you will have for the gradient at 1 comma 1, but then I ask you what does it mean. So generally people find it hard to answer this question. So in this video we will try to describe what does that mean, and eventually at the end of the video you will be able to say what does it mean. So let's start. So here I have a gradient, so let me describe it. Gradient operator. I need to take care of something, and that is my handwriting. So because my handwriting is very poor, so let me write slowly. Gradient operator. I hope this is readable. Sorry, I do bad jokes. So gradient operator. Now before talking about gradient operator, let's just discuss in one dimension what does it mean, because gradient operator generally people think is in higher dimension. So let's try to reduce the number of dimensions and think what does it mean in one dimension. So in one dimension we have derivative, right? Derivative of a function, right? We have a derivative of a function. So suppose I give you a function f of x which is equal to y, and I ask you to compute what is f prime of x at x is equal to x0. So this is by notation, it is written as d by dx f of x at x is equal to x0, right? Okay. So and the fundamental definition is, so here is the fundamental definition. The fundamental definition is f prime of x0 is limit delta x tends to 0 f of x0 plus delta x minus f of x0 divided by delta x. So that is the fundamental definition. So let me box this equation because this is an important equation. Very good. Okay. So this is the fundamental definition. So now what does it mean? So again the question is, what does it mean to take a derivative of a function at a particular point? Suppose I give you a function, let's say x square plus 3x plus y cube. Oh, sorry, not in y cube, because we are talking about in one dimension. So suppose I give you a function like x square plus 2x. So then I ask you to compute what's the derivative of this function at point x is equal to 1. Then you will give me an answer, let's say 4. Then I ask you the question, what does it mean? So we will discuss that. What does it mean? Okay. So what does it mean? Question is, sorry. What does it mean? And I'll be asking this question very frequently. What does it mean? So stay with me. So here is my function. Let me use a different color. So here is my function, and let's say this is my point x is equal to x0. And I ask what it means to have a derivative of this function at a particular point x is equal to x0. So you clearly know the answer is probably very simple, and the answer is that it's the slope of the tangent, right? So let me draw a tangent line here. I hope this is a tangent at this particular point. Better. Probably this is better. So let me change this point to somewhere here. So my derivative at this particular point means the slope of this tangent at x is equal to x0. So if this line is making an angle theta with the x-axis, then my tan theta would be f prime of x0 at this point, and that is actually equal to the slope m. So let me denote the slope by m. And you know why this is true, right? This is a very simple thing. So let me box this equation, because this is also important. So when somebody asks you what does it mean that you compute the slope of a function at a particular point in one dimension, it means that it is the slope of the tangent at that particular point. Okay, so let me give you an example. I mean, examples are always great because they say everything in a very compact form. So for example, I have a function f of x which is actually equal to x square plus 2x. So the question is, what is f prime of 1? That's the question. So you clearly see that f prime of x dx is equal to d by dx of x square plus 2x, and that is actually equal to 2x plus 2, right? And f prime of 1 is equal to 2 plus 2, which is equal to 4. So f prime of 1 is equal to 4. So what does it mean? That if you draw this function, and let me draw it actually. So let me draw f of x is equal to 2x plus, I think this would be a simpler function. Let me take x square plus 2x plus 1, because that's easy to draw, plus 0, and that will give me 4. Answer is 4. So this is y, and then we have x square plus 2x plus 1, which is actually equal to x plus 1 to the power square. And the function, so let me draw this function. Very good. And so this is x plus 1 whole square. So when x is equal to, so this is when x is equal to minus 1, y is equal to 0. So when x is equal to minus 1 is here, let's say minus 1, and it is always positive. It's always positive, and it's also a parabola. So let me draw this function, and we have it's a symmetric about x is equal to minus 1 axis. I'm very bad at drawing. Okay. Oh, fine. Oh, what did I do? Sorry. So this is my function, and so at x is equal to minus 1, y is equal to 0, right? Okay. So then I asked what is the slope at x is equal to 1. So this is my x is equal to 1. Oh, probably I have x is equal to 1 would be a very Let me draw this in a very different style, so that I can at least tell you what does it mean. Okay, so this is so far it's fine. I mean, you understand what I am talking about. So at x is equal to 1, this is my x is equal to 1, and therefore the slope of this tangent, that is the tangent at this particular point, the slope of this tangent line, the yellow one, that theta, that tan theta would be 4. That is my slope of the tangent. That's what it means. Okay, so far so good in one dimension, right? So let's go to higher dimension, because that's what we want to talk about. So in higher dimension, we want to talk about what's called a gradient, because generally in one dimension we call it derivative, and when we go to higher dimension we call it a gradient operator. So let's say in 2 dimension, so let me give you an example first. So suppose I have a function f of x which is equal to x square plus y square. Let's see, this is an easy function. X square plus y square is symmetric in x and y, and then I tell you figure out what's the gradient of this function. Sorry, this is x is a function of x and y. Now the question is the gradient equivalent to taking derivatives? Is the gradient is taking gradient of a function equivalent to taking derivative in one dimension? And the answer is no. It's not. It is not equivalent. And let me answer that first, and then we will tackle this question. So you see that in one dimension, right? So you see that in one dimension, when I talk about taking the derivative of a function at a particular point, right? So for example, taking the derivative at a particular point, let's say at this point x is equal to 1, then what options do you have? So the operation of taking derivative is that you stand at that particular point and then you move a little bit away from the particular point, then you take the difference of those functions, you evaluate those functions at those particular points, and then you take the difference and then you divide by the increment by which you move. That's what it means, right? So let me actually write it. So the act of taking derivative, we'll come back to this 2-dimension version, but the act of taking derivative, what does it mean to take derivative? Is you take the function, you evaluate the function at a nearby point by moving your point from x0 to x0 plus delta x, and then you take the difference and then you divide by it. That's what the general operation of derivative means. And then you take the limit in which delta x tends to 0, so such that you get the you get your derivative. Okay, but you see that when I say you to figure out to figure out the derivative of a function in one dimension, you only have one direction to move. Either you start from you start at a particular point x0, either you can move in the forward direction or either you can move in the backward direction, right? There is no ambiguity. There is only one dimension in which you can move, so there is no ambiguity in computing the derivative. But when it comes to 2 dimensions, then you have a lot of options, because again that you see here, that here is my xy plane, here is my, let me draw this axis. Very good. So let's say that I want to compute at this particular point x0 y0. This is my x0 y0 point, and I want to compute the derivative at this particular point, right? So now the question is, which direction should I move? That's the question, right? Which direction should I move? Should I compute the derivative in this direction, or should I compute the derivative in this direction? Should I compute the derivative in this direction, or possibly along this curve, or in different curve? So there are infinite number of directions in which you can compute the derivative. So therefore the act of taking gradient and the act of taking derivative in 2 dimension is a different thing. In 1 dimension and 2 dimension is a different thing. So the equivalent of taking derivatives in 1 dimension is something, in 2 dimension we call it directional derivative. because direction matter. Directional derivatives. Derivative. So the everything boils down to computing the derivative in a particular direction. For example, suppose I give you a point x0 y0, then I also have to tell you in which direction I am moving towards x0 y0. That's extra information that I have to give you. In one dimension I don't have to give you that, because there was only one single line that you are restricted to move. But when you go to two dimensions, there are infinite number of ways in which you can approach to x0 y0. So I have to tell you the information that in which direction I am computing the derivative. So therefore let me give you a direction in which I am computing the derivative, and let me give you an arbitrary direction. Let's say this direction. This direction is given by u cap. This direction is given by u cap. The cap represents that we are talking about a unit vector. So I will give you u cap, which is actually equal to a ex cap b ey cap. What are my ex and ey cap? Ex cap and ey cap are unit vectors in x and y directions respectively. Okay. Some people denote it by I and j, but I denote it by ex and ey, because as you go in, basically it's my notation. Fine. Okay. And what is the magnitude of u is 1. So therefore a square plus b square, square root of that is actually equal to 1. Fine. Okay. So now I have to move, since in this direction, right? I have to move in this direction. Therefore because I am computing my directional derivative along this direction. So what does it mean? What it means is that suppose I have a function f of xy, then I am asking that if I move along this direction. So what I'm saying, that suppose I have a function f of xy, and if I move along this direction u, what is my rate of change of the function? That's what I am asking. So I hope you understand this question for what a directional derivative means. Okay. So directional derivative means it requires to give you an extra additional information, which is the direction, and why we require it, because we want to know that if I move along this function, what is my rate of change of the function. Okay. So let's compute the directional derivative in u direction at a particular point x0 y0. So it means that if I stand at particular point x0 y0 and I move along this direction u, how does my function change? What is the rate of change of my function? Okay. So because I'm repeating myself, but this is very important. Okay. So this is my particular point x0 y0, right? And let's say x0 y0, and let's say that I move to a nearby point x comma y, right? This is this x comma y. So let me draw this vectors here. This is my another vector. Let me draw it by different color so this will be visible. This u, so let me, because I want to make a good sketch, please bear with me. And so I have to draw this another vector, so let me use a different color, and this is another vector which would lie on this line, on this vector u. So this is my vector. Okay. So this point is given by x0 y0, and this point is given by some x comma y, right? So I have to figure out the equation of this line. That's what I am doing all this. So the equation of the line would be x minus x0 ex or x minus x0 y minus y0, this vector should be in the direction of u, right? Because this vector x minus x0 y minus y0 is this vector, this one, and that should be in the direction of u, so t times u. Okay, so if I separate it out, then I will get x minus x0 y minus y0 is actually equal to t a ex cap plus b ey cap, or in my notation this is just a comma b, right? And if you compare, then you will find x is equal to x0 plus at and y is equal to y0 plus bt. So these are my coordinates, on the in the u direction. That means that if I move in the direction of u, then my x and y coordinates are given in terms of x0 and y0 and a and b. Okay, so the directional derivative is denoted by directional u cap, du cap. What does it mean? That I am computing my directional derivative in the direction of u, and then of a function f, and at a point x0 y0. So that's what the whole notation means. I'm computing my directional derivative in u direction at a particular point f and in the direction of x0 y0, at point x0 y0. Okay, and that, whoa, and the question is what is that? So let me actually derive this for you, because this is very important. So again, we will use the fundamental definition of our derivative. So we will say this is equal to limit t tends to 0 f of x comma y minus f of x0 comma y0 divided by t, right? Because, and why is that? Because f of x comma y would now be a function of t, and because we will put in place of x and y, we will put x0 plus at, and y, and in place of y we will put y0 equal to y is equal to y0 plus bt. Okay, so this would give me, so this is nothing but df by dt, right? This is nothing but df by dt, because it's just a function of derivative with respect to t at t is equal to 0. Now, because this is just a function of t, right? This you can also represent this nothing, but this is just a function of t, some function of t, and this is nothing but g of t0, right? Because at g at t is equal to 0. Because at t is equal to 0, your x is equal to x0 and y is equal to y0. So this is why I have written it as d some df by dt. You can write it dg by dt also. Okay, so this, by chain rule, it is nothing but df by dx at x is equal to x0. Sorry, so this would be so here let me expand this. This is d by dt. This is f as a function of x comma y, but this is x is equal to a x0 plus at, and y is equal to y0 plus bt, and we have to evaluate at t is equal to 0, right? So by using chain rule, this is nothing but df by dx into dx by dt plus df by dy into dy by dt at t is equal to 0. So at t is equal to 0, right, this everything at t is equal to 0. So at t is equal to 0, my df by dx, this will be evaluated at x is equal to x0, and this guy is nothing but, this is a, because this is d by dt of x0 plus at, and this is df by dy at x0 y0. Okay, let me not skip a step, because if I skip a step you will get confused. This is nothing but a function of x0 plus at y0, x0 plus at y0 plus bt into d by dt of x0 plus at, and this I have to evaluate at t is equal to 0, and plus other term which is df by dy x0 plus at y0 plus bt d by dt of y0 plus bt, and that should also be evaluated at t is equal to 0. So when I evaluate this everything at t is equal to 0, I get df by dy at x0 y0 into a plus df by dy x0 y0 at b, right? And in we know that your u vector is nothing but a ex cap b ey cap. I can write this as df dx ex. I can write this as ex at x0 y0 plus ey x0 y0 dotted with aex cap plus bey cap, and this I call it gradient of f at x0 y0. So at last what I get, that my directional derivative in u direction, right, derivative of a function f in u direction at a point x0 y0 is nothing but the gradient of the function at x0 y0 times the unit vector, and this is a very important equation. Let me put that in the box. Very good. Okay, so from this equation we get a hint of what a gradient is. From this equation we get a hint of what a gradient is, and why I'm saying that, because you see that what does this represent? This represents rate of change of my function f in the direction of u, right? That's what it means, that how my function is changing if I move in the direction of u. That is the rate of change of my function in the direction in the direction u. Okay, so it says directional derivative in the direction of u at a particular point x0 y0 is, if I write in terms of magnitude and cosine theta, then this is gradient at x0 y0, magnitude of that u magnitude times the cosine of theta, and theta is the angle between u and the gradient of and the gradient. Since my u is unit vector, so therefore mod of u is equal to 1. Therefore I get directional derivative in the direction u at a point x0 y0 of the function f is nothing but the magnitude of gradient times cosine of theta. This is also an important equation. So it says my rate of, this is very important, please pay attention, my rate of change of function is maximum if I move in u direction. If I move in u direction, which is parallel to gradient at that point. So the summary of this equation is that, so which corresponds to theta being 0 degree. So what it means that if I am standing at a particular point x0 y0, I compute the gradient at this particular point of some given, so I am given a function f of xy, and I compute my gradient at a particular point x0 y0, then it means that if I move in this direction of the gradient itself, I am going to get the maximum rate of change of function of my function. So it says that if I compute my gradient at a particular point, and the gradient is the direction in which the function changes the maximum. Similarly, you can also say that if I move in minus the gradient of x0 y0, the rate of my function will decrease the fastest. That's what it means, that if I choose in the opposite direction of the gradient at a particular point, my function, the rate of change of the function would be the steepest. Or what it means is that my function will decrease maximum in this direction, and in the direction of gradient, my function will increase the maximum, will increase the fastest. So let me give you an example. So let's say the example we are going to discuss is f of xy is equal to x square plus y square. So, and I compute, that's what I want to compute. So what do? Gradient of f of x comma y is ex df by dx plus ey df by dy, which is actually equal to ex df by dx x square plus y square ey d by dy x square plus y square, and that is nothing but ex, this is this 2x plus 0 plus ey 0 plus 2y, so which is basically ex 2x plus ey 2y, and that is my gradient function at x comma y. I want to compute at 1 comma 1, so this is 2ex plus 2ey, right? So what it means, that my gradient at a particular point 1 comma 1 is 2ex and 2ey, and if I move along this direction, my function, the rate of change of the function will be maximum, and if I move in the opposite direction of the gradient minus the direction of the gradient, then my rate of change of the function will be the minimum. Okay, so let me give you the diagrammatically what's happening in this problem. So my function f of xy is x square plus y square. Let me draw some level curves. What are level curves? Level curves are just curves that satisfy f of xy is equal to some constant. Those are level curves. So if you're not if you're seeing this term for the first time, just think of just you have seen those maps of the mountains in which you have given all the curves of a particular height, right? So at a particular height, there will be a curve designated to that particular height. So if you move along that particular curve, your height is not going to change. So these are the same kind of thing that we are doing here. So f of x comma y is equal to x square plus y square is equal to some constant. So of course this constant is positive. So what are these? These are circles in xy plane, right? So let me draw those. Let me draw a couple of more. So let's say this corresponds to x square plus y square equals to 1. This, let's say, correspond to x square plus y square equals to 4. And let's say this corresponds to x square plus y square equals to 9. So what I have asked you, this is x-axis, this is y-axis, right? So what I have asked you is to compute this guy, 1 comma 1. So 1 comma 1 would be, 1 comma 1 doesn't lie on this any of this circle. So let's say 1 comma 1 is actually this correspond to x square plus y square equals to 2, because then 1 comma 1 would lie on this particular circle. So 1 comma 1 would be here, somewhat here, right? And this came out to be 2ex plus 2ey, and that vector would be just look like that, right? At this point is 1 comma 1, and that vector is 2ex 2ey. These are not drawn to scale, but you get the gist of it, what I'm talking about. So what it says is that, and these are my level curves of this function, right, f of xy. So what it says is that along this entire white circle, my value of the function is 2. Along this, my value of the function is 4, and along this circle, which is the green one, my value of the function is 9. So at 1 comma 1, I have drawn this arrow. So what it means is that if I move along this particular direction, the gradient at this particular point 1 comma 1, in this direction, my function is going to change maximum, and in the opposite direction, my function is going to change in the minimum. So that's what gradient means. So basically, let me summarize what I have taught you in this video. So in this video, what I have taught you is that when you go from one dimension to two dimension, then the question of taking derivative is not so easy, because you have infinite number of directions in which you can move, and therefore what comes there is something called directional derivative, in which I have to give you an extra information that in which direction I want you to compute the derivative. That's why we call it directional derivative. And I also gave you the meaning of what directional derivative is. I also derived you the expression for directional derivative for you, which is this one shown on the screen. And then then from there, using the definition of directional derivative, I actually taught you what does gradient mean. What does gradient mean? If I compute the gradient of a function at a particular point, what does it mean? It means that in that direction the function is going to change maximum, and in the opposite direction the function is going to change minimum. The rate of change of function would be maximum in the direction of gradient, and the rate of change of the function would be minimum in the opposite direction of the gradient, which is minus the gradient. That's what I have shown you. Then I have drawn some level curves for you, and then I have showed you that at this particular point, if you're standing at this particular point at 1 comma 1, and I want you to compute the gradient at this particular point, then it means that if I move along this direction at 2x 2ex plus 2ey, I am going to get the maximum rate of change of my function f of xy, which is equal to x squared plus y squared. Okay, then I think this video is taking very longer, so let me just finish it off with some generalization. Generalization to higher dimensions. So the generalization is easy. It's very easy. So the gradient in n dimension is nothing but ei xi summation over I. That's my operator, gradient operator. And when it acts on a function, let's say this would mean, so ei is the unit vector in the ith direction. There are n unit vectors. This is what it means. And at a particular point, let's say a1, a2 up to an, this means a1, a2 up to an. And the meaning remains same. That if I go to this particular point a1, a2 up to an, and I compute the gradient, this means that in the direction of the gradient, my function is going to, the rate of change of the function will be maximum, and in the opposite direction, the rate of change of the function will be minimum. That just comes from the definition of directional derivatives. You can also generalize the definition of directional derivatives. So the generalization would be, so that will be the definition of derivative in your n dimension. It means that directional derivative in my u direction of the function f at a particular, let me denote it by a vector. So a vector means that a1, a2, a3, a2 up to an. This is nothing but the gradient f at particular point a dot with u. That's a generalization. And it simply means that it simply gives you what is the rate of change of my function f in n dimension if I move in u direction starting from point a. That's what it means. That will give you the rate of change of the function at particular point a if you move in the u direction. Okay, so with that I will end this video, and in the next video we will talk about divergence, and we will talk about curls in the upcoming videos, and then we will also generalizes this idea to different coordinate systems that we use mostly in physics, which are cylindrical coordinate system and spherical coordinate system, because there the expressions get complicated because the unit vectors are also functions of function of your, because the unit vectors also become function of coordinates, and therefore the expressions get a little bit complicated, and we will derive those expressions, and we will see what does gradient mean, what does curl mean, and once we know what they mean, we can just work out with the mathematics. So with that I will see you in the next video. Thank you.